right now.
Hello.
Say your famous words.
Gypsy magic.
All right, so let's get this. Let's wrap up chapter 14 here. Walsh diagram. There's some orbitals on this side. We recognize their symbols, pi's and sigmas, and that's just because that's for diatomic molecules, and we're going to see this a lot more in chapter 15. This way, this representation, this notation for molecular orbitals. So don't really worry about the A's and the B's right now. And they're just showing how molecular orbitals energies, they change as you change molecular shape and things. And that's expected. Okay. The few more terms here. We've talked about bonding orbitals. We've talked about anti-bonding orbitals. Well, now there's going to be some that are right on the cusp, right at the same level as the orbitals that you're adding in the first place. So they're not going to help you, and they're not going to hurt you. So non-bonding, right? They're right at the same level as the orbitals that we're mixing in the first place to create the molecular orbitals. Okay. You've used the word conjugated in organic, right? Especially with what molecule? It has conjugated bonds. Instead of drawing it out, you drew a little circle in the middle. Benzene ring, right? Aromatic, right? This conjugation, what does that mean? That means what? You have alternating double bond and single bond, right? But they don't stay there, right? It's kind of shared all over the place. But it is. It's supposed to be alternating double and single bonds. Okay? So that's kind of the same idea as this delocalization energy, right? That the energy is actually lowered by doing this. Okay, this extra stabilization. Huckle approximation. This is kind of the lazy way. I guess in getting with Spartan, what I'm talking about is for getting like vibrational energies, all these molecular calculations you can do, molecular shape, ionization energies, all this stuff. Well, if you have a really slow computer, and they did at times, right? You know, things weren't always where we are right now. And they said all overlap integrals are 0. Let's just throw them all, make them all 0. So that's what the Huckle approximation was. I just called it the lazy way because it's so much, everything's 0 pretty much, so not a whole lot to do. Okay, here's some terminology that I wish they would have changed, but they haven't. So what is this stuff? They call them frontier orbitals. There it is. HOMO and LUMO. Highest occupied molecular orbital and lowest unoccupied molecular orbital. Why is this the big deal? And they even throw the word frontier orbitals on it. Because this is where your first transition is going to occur from. Right? Whether you're talking about absorption, right, or something like that. It's going to go from your highest occupied, should be the other way around, right? Have the highest occupied molecular orbital on the bottom. And that would be your first transition. Okay. And so this section in here, this is a lot of talk with, if you really got into Spartan and all the little check boxes and all those sorts of things. What modifies, what parameters do you have in these modeling calculations? And here's, I can feel it getting warm in here already, can't you? But it's on. All right, it's on now. So you could check this little box, semi-empirical methods or ab initio methods. Which one are you actually kind of cheating on? You're throwing in fudge factors, like maybe all the ionization energies or vibrational energies. You're cheating. You're taking experimental data and you're giving it to the computer so it can get even better guesses. Yes. Semi-empirical. Semi-empirical is the one where you're throwing in some fudge factors. Usually it's ionization energies. And then ab initio is the one you're just starting right from scratch. You're calculating everything. It's ab initio methods. Okay. So CNDO, it's if you have different nuclei, right? They're different. I'll pick A and B. You could have a lot more, but the point is the nuclei are different, and you ignore their overlap, but you don't. Those are the only ones where you say the overlap integrals are 0, all of them, if the nuclei are different. So they're just trying to play around with things and try to arrive at the best answers the quickest way. But now, I mean, computers are getting so good, ab initio is getting more and more and more. A Gaussian type orbital, some constant r squared, something in that format. They use it a lot in ab initio. But, okay. Now here, band theory of solids is something a little more applicable that you can probably put your hands around. I remember, man, it wasn't that long ago where we were actually using typewriters, right? Where you go to a college and they have, college typewriters you have to plug in and stuff, right? So it wasn't really that long ago. Same time frame is when you go to the college and, this is where they have the computers. And they're in these super frigid rooms. I mean, they had these big rooms, glass windows around everything. This is a really big deal. Ooh, look what you have, right? University of Minnesota. Ooh, look what you have. And I got to go there and touch the glass and stuff. Everything's all nice. It's always nice and cold in that room. Why? Why? Now our material science is better now. We're making better semiconductors now. But back then, what's the deal? Okay, now it's something with temperature, right? If you increase the temperature of a semiconductor, what happens to its resistance? We're going to stick to the word resistance because that's what the book uses a lot. The resistance goes up or it goes down as you increase the temperature. For a semiconductor, it goes down. It's just the opposite of what you would think, right? I would think if you crank up the temperature, things are moving around, right? All this more energy, everything's moving around. It's going to be much harder for current or electrons to get, or charged particles to get from one end of the material to the other because things are moving around so much, right? So I would think resistance would increase, but it's just the opposite for semiconductors. Band theory answers that. But the point is that the reason for that big long story was that you're going to have runaway, everything's going to burn out and short circuit on you, and it's going to, because the resistance drops to nothing when it gets hot. So things aren't going to work for semiconductors. For resistors, for metals, things, tin, aluminum, iron, whatever, they conduct electricity, and if you crank up the temperature, their resistance goes up. Okay? Band theory of solids is going to tell us why. What's an insulator? Like, what's an example of an insulator? Rubber, glass, styrofoam. Yeah, stuff that doesn't conduct electricity. Why? They're all solids. Why? Why don't they conduct electricity? Band theory of solids is going to tell us why. Okay, so those three things are going to be covered in this stuff. Okay, so when you look at this diagram, just jumping ahead, there's bands. These energies that are just so close together, there's no gaps at all in there. I mean, they're just one on top of another. That's what we're generating or calculating. How? this is what they're trying to illustrate over here. So if you have one atom, right, you get one orbital. If you have two atoms, you get two orbitals. All they're saying is each atom in this theory is donating one orbital. And they're just going to throw them all together, and just like we do for molecular orbital theory, you just, you mix them up and create the molecular orbitals. Well, we're not talking about molecules, we're talking about solids, so same idea though. Well, all the atoms there are donating orbitals in this theory, and it's working so far. So the more orbitals, the more atoms you have, the more orbitals you're gonna be getting. But notice what's happening as you donate. Like if you donate if you have two atoms, two orbitals are donated. Do you see that? Here's your result. You get a definite separation of energy levels between these two band orbitals. It's not really a band yet, but we're getting there. But one is anti-bonding, one is bonding. So that's what's coming out of this. If you mix three orbitals, now we get a bonding, a non-bonding, and a anti-bonding. Now it doesn't look anything like a band because you can see the gaps between the orbitals. So you just got to keep adding them, keep adding. And just like all solids, man, there's a gazillion atoms. So you get a gazillion levels, gazillion orbitals. And now you can't see any energy difference between them. You have a band. Okay? So, but notice in that band, I mean, you have bonding and anti-bonding and all that stuff going on in there. Okay, so what they want you to think of now is you have these bands. You have this. That's what they're talking about, a band. And if it's this material will be classified as a metal if that band is full or not full of electrons. Now, remember metal. The only thing that I can keep this straight of is metals conduct electricity really easily, right? So that means, what you're kind of missing is for electricity to be conducted in this type of theory, you need space, you need holes, you need orbitals. For these electrons to jump around and actually move from one end to the other, you actually need molecular orbitals, open orbitals, for them to jump into and get transmitted and then conduct across material. So if it's a metal, conducts really, really easily, would you want the band full? No. So that's all metal is. They're saying the band's not full. So it can easily conduct electricity. And then you crank up the temperature. Well, man, now if the temperature is really, 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 really low, their theory is always, remember, it's theoretical. So they're always saying T equals 0. Probably what units for their 0? Not Celsius, but Kelvin. So they're talking about absolute 0. So absolute 0, you've got all the electrons hanging out, right, the bottom part, and you have if I could erase it, I'd erase this top part up here, right? And yeah, so it's at 0 Kelvin. Ooh, it conducts really, really well. Well, you keep raising the temperature. Now those electrons are getting promoted up into those orbitals that I drew in red, and they're kind of starting to mess stuff up. They're getting in the way, so you're going to get some resistance going on there. I mean, it still conducts really, really well, but the conduction goes down a little bit because now there's some resistance. And the more you heat it up, the more resistance there is. But it still conducts really, really well. Look at the copper. Copper hot. Does that matter? No. Not really. Okay. So that's for metals. Make sense? Okay. Semiconductors. In order to talk about semiconductors, it's the same idea. You're generating all these bands. However, what I wish they would have done is they would have said, even in this one, you've got bands all over the place. It doesn't mean that they're occupied. Right? It's just kind of like saying if we do our electron configurations, 1s, 2s, 3s, we could write 5D if we wanted. But there's nothing in there. But you could write it, right? Just like when you're talking about the metals in this band theory. We could write more bands. They're just, who cares? They're not there, right? They're not being used, and you don't even care because the band you're in isn't even full, right? So with semiconductors, though, these other bands are essential to explain what's going on. And they got to be somewhat close. And all these parameters got to fall into play for it to be a semiconductor. So that's why there's not that many of them, because things have to fall in just right for it to be a semiconductor and have those properties of a semiconductor, where resistance drops as temperature goes up. Okay. So in a semiconductor, you've got, to explain it, you've got two bands. One is full, the other one empty. And they're going to call this a valence band, the bottom one, the top one a conduction band. And they're separated by a band gap. Right? So as you crank up the temperature, those electrons just get promoted from what band to what band? Valence to conduction. They conduct really well. Right? There's nothing, it's very free up there. So that's why resistance goes down as temperature goes up for a semiconductor. Okay. Now I didn't sketch one in for insulator. I didn't sketch in a band idea for insulator. But what would it look like? Definitely the bottom one has to be full. The band above it has to be empty. But exactly what Rob said, really far up there. That band gap is huge. Doesn't matter how much you heat it up. They can't jump into it. It's just too high. And that's how they explain the electrical differences between a metal, semiconductor, and insulator. And we just have to introduce some terms into all this now. Explain it the way they explain it. One is Fermi level. Pretty much, I could say that's HOMO. What does that stand for again, Sandy? Highest occupied molecular orbital. The Fermi level, right? So in the Fermi level for a metal, right, might be, the Fermi level for a metal might be somewhere in here, right? So that you see, it's just not full. The Fermi level for a semiconductor is definitely right there, right? It's just the highest occupied molecular orbital. Okay. What other terms do we have here? Oh, S band and P band. This terminology is coming from, in theory, what type of orbitals is each metallic atom donating? Is it a 1s, a 2s? Well, if it's a 2s type orbital, you call it an S band. If it's a 3p orbital, you call it a P band. So that's where this stuff is coming from. Just what type of orbitals were these atoms in the material donating in the first place? Remember, each atom donates one orbital in this theory. So if they don't have that listed, so they must not be. Right? I've never heard of it. I'm curious why. You should Google it. Okay. Okay. And here's what they're trying to say. Remember, you're adding these guys. Here's bonding, non-bonding, anti-bonding. And they're just trying to show you what they look like, right? For anti-bonding orbitals, the sign is changing all the time. There's destructive interference, however you'd like to think of it. Okay. And the same with, that's what the S band. The P band, they just kind of drew those PZ orbitals and overlapped them to show that, hey, you have constructive or destructive interference with them. And remember, the different colors just represented different signs of the wave function. So when you have the same sign, you'll have constructive interference. Opposite signs, opposite colors, destructive interference. Okay. Here's they're indicating the Fermi level. We kind of already jumped ahead and told that one. Right? It's kind of the HOMO. Okay. Now, and they are often, I don't know, keep forgetting that, but that's that T is 0 Kelvin is their Fermi level idea. Very often talking about that. But okay. Here, this is kind of hard to see out of this, but in that plot, this is one way that they use to explain and to quantify what we're doing a lot of hand waving here. Saying, oh, at this temperature, now we're going to get so many electrons so much promoted into the conduction band, right? And it's going to start conducting. Well, at what temperature does that happen, and just how much does it happen? That's what this Fermi-Dirac distribution is kind of like. So it,
Is that like upside down and reflected?
it does look. I wouldn't really worry about it. I'm not expecting you to read it, but it does look. It does look like it's reflected different, doesn't it?
Yeah.
Wow. I don't think I can flip it. Oh. Right? You can't. I need to reflect it. I can't reflect it. All I can do is rotate. I need to flip it. Oh, maybe I can do that. There it goes. Yeah. Okay. All right. Why do we not need cold rooms and all this stuff anymore? They figured out some stuff, all right, for these computers. We can control these semiconductors and modify them. And how do you do that? Remember, how do you get conduction? Right? Go back to this metal idea. Right? There was space up there. In a band for a metal, there's space for those electrons to move around. They call those holes. Holes. That's the terminology they use. There's holes. So these electrons can do their thing. Conduct very easily in a metal. There's holes in the band. So if you have a semiconductor, there aren't any holes. But let's introduce them by doping. Let's replace some of those atoms. Because remember, in a semiconductor, what type of material are we talking about? Is this like a hunk of glass that's kind of all amorphous and there isn't a whole lot of repetitive shape? Or is it the opposite extreme of crystal? What is a semiconductor? It's a crystal. They're crystalline. So you can replace in that crystalline structure, that lattice, remember all face-centered cubic, body-centered cubic, there's a whole bunch of different types of lattices. We're not interested in that. I'm just trying to get you to remember what a crystal was, right? So in that crystalline shape, in that lattice shape, always replace this atom with sulfur or something where it's going to have one less electron. It's going to donate one less electron to the pile. So you're going to generate some holes. That's p-type semiconductivity. Well, what's the other type? Well, instead of creating holes, let's just throw in extra electrons. Because remember, for a semiconductor, your Fermi level is right here. So in that crystalline lattice, let's replace some of those atoms with something that has more electrons than silicon. All right, I have the periodic table. Pick something that has more electrons. And then they're going to be up here. And you're controlling all this. So you can control the conductivity of your semiconductor, of your material. Much more stable, much more controlled. Okay, so that's N-type semiconductivity. Okay. So we have not a whole lot of homework here. Give the parities of the 6 pi molecular orbitals of benzene. I have hint, use figure 14.44. Oh yeah, it's right here. Okay. Give the parities. Oh, hang on here. See if you remember this. Here's a test question. Give the parities of the 6 molecular orbitals of benzene. Okay. If it's asking for parities, benzene has to have a what? Otherwise, it can't have parity in the first place. Benzene has to have a what? What symmetric property? Well, yeah. That, if you have a diatomic molecule, they're both the same. It has that symmetric property. What is it called? Center of inversion. Right? Center of inversion. Does benzene molecule have a center of inversion? It has to, because this thing's asking for it. But how? How do you draw? I've never been very good at drawing this. Right? But reflect each point through the center of this. It's the same. Right? It's the same. No matter how you reflect it through the center, it's the same. So benzene does have a center of inversion. So benzene's molecular orbitals are going to have little G's and U's, Gerada and Ungerada on them. Well, I have no idea what they are, so that's why we have to look at figure 14.44 for the little pictures. Let's see. 4.6. Okay, here's 14.44. Okay. There they are. So we have A2U, E1G, E2U, and B2G. So we have to look at these pictures, identify if there's a center, identify if it's Gerada or Ungerada, right? Gerada was where no sign change. Ungerada is where there was a sign change. And with these plots, they don't have little pluses and minuses, so you have to go by, you know, like pick their dark as negative and their light as positive sign or something. Right? So if you look at like A2U, reflect through the center, does it change sign? No. So A2U would be Gerada. Isn't that weird? What is the U doing down there then? But anyway, I don't know. See what I'm saying?
Gypsy magic.
So A2U will be Gerada. Make sense?
No, but
Yeah, there is, because A2U. The U must obviously means something else. So there's obviously means something else. That's on page 416. We'd have to Google it to find out exactly what that little U means. Okay. But so benzene has these molecular orbitals: A2U, E1G, E2U, and B2G. Okay.
I think they just kind of threw darts at the board. There was one question.
We'd have to really get into this. I don't think they even said it in here. I don't remember reading it. Well, it's just like, it's the same idea as other molecular orbitals we're going to see. 3A1. What does the little 1 mean? Right, what does the A mean? What does the 3 mean? I think chapter 15 is going to give us a lot more insight into this, but even that may not give us all the answers. Just like saying 2s. Why s? Right? Like in the hydrogen orbitals, 3d. Why d? Right? You have to Google it. I'm not sure why. See what I'm saying? So why A2U? Because they said so. I agree. So all you say is just, who cares what they call it? Is it Gerada or Ungerada? A2U is, yeah, I lost the page already. I think it's Gerada, right? It didn't change. It was all this, A2U was all the same color, so it had to be Gerada. Yeah, page 416. So do that for every one of those on page 416. So that's not so bad. How about number 12? Predict the electron configuration. Oh, we're using the same figure. It's the same. I don't see.
So there's two E1.
Well, yeah, there's yeah, but they have the same parity. They have the same parity. Okay. Okay. Predict the electron configurations. Benzene anion. So again, it's odd. We just need to get used to writing electron configurations with molecular orbitals. We're used to doing it with using hydrogen orbitals, like 1s2, 2s2, that sort of thing. Now we have to get used to saying, oh, A2U with a superscript, E1G with a superscript, but recognize how many orbitals does A2U have according to this plot. There's just one. E1G has how many orbitals? 2. So you're going to fill up E1G, who's going to have a maximum superscript of 4. A2U is going to have a maximum superscript of 2. And you got to fill it up before you start filling up E1G. And then E2U is going to have a maximum superscript of 4. B2G would be 2. So if you want to do the, how many valence electrons do we have here? We've got benzene, I lost it, benzene anion. Benzene anion. Okay. Now this is supposed to be benzene. So they're saying benzene has how many valence electrons in the first place? 6. Well, how'd they get the 6?
Double bonds. There's 3 double bonds, so 3 2s. Double bond, double bond. I'm just trying to make sense out of the gypsum H fan. I don't care.
Maybe they are talking about just the delocalized stuff. Is that what that is? That would be the 6. Bond of the delocalized orbitals. Yeah, I think you're right. I think they're talking about, yeah. Okay. See in the middle of the page 416, the electron energy of benzene is, now where are they getting this stuff from? So they're talking about the pi electron energy. So you're right. It's that delocalization energy, that stabilization energy. So there's just those pi electrons, and you have 3 double bonds, so it's going to be 6. Okay. Oh, it does. Pi bond energy. Okay. That's how they're getting their 6. Make sense? Okay. So this is benzene. You put in 6. And then we're going to need, might as well follow this, the rest of this diagram, because we're going to need it for the rest of this question. If you look at the middle of the page, okay, they have 2 times alpha plus 2 beta. So that means A2U, his energy is alpha plus 2 beta. And it's 2 times alpha plus 2 beta because you have 2 electrons in there. And then you have E1G. Well, his energy is alpha plus beta. But you have 4 of them in there, so you have 4 times alpha plus beta. And then E2U, what's his energy? It's alpha minus beta. So we only have a, we don't have any in there, so we're done. So that's why he stopped. That's why he stopped. But for us, no, we don't have benzene. They wanted benzene anion. So we have to write the electron configuration of, add an arrow where? Way up here, E2U. So you're going to write, you're going to fill up A2U, you're going to fill up E1G, and then you're going to have an E2U with a superscript of 1. That would be your electron configuration for the benzene anion. Right? Make sense? Then you need to, then I might as well just calculate, well, let's just finish this. The benzene cation, take away 1, and write its electron configuration. Yeah, it'd be E1G3 would be the top one. Okay. Now, you don't have a book. You don't have any idea what we're talking about. You should get your tail over here and take a look at this, right? We only have one book. We only have 2 books. All right. So, Anna, Adriana, come over here and take a look at these books. You don't have a clue what they're talking about. We have to Google it. We have to Google it to see what it means.
Yeah,
because it's
look
not.
At another page before where it's talking about like grata and grata. That one and another one before. And if you look at the colors that are used in the figure that we're looking at and the way it's going, I feel like the U and the G.
See, like here, grata means it's not changing sign. It's not changing color. So we have to follow the same format to identify the parity in benzene. However, with molecular orbitals, this is their convention. They only put the parity on diatomic molecules that have a center of inversion. So all the other molecular orbitals you're ever going to see in your life, there could be a G or a U on it. Like, who knows what the hell they're coming up with for their notation. But that does not mean parity. It only means parity for diatomics. You think they'd come up with a better way of doing this, but that's how we have to live with it. So, okay. So then we need to calculate the pi bond energy in each case. So using your electron configuration, do what the book did for benzene. Right? They said in the reading here somewhere. I found it. So I said that A2U is, you can write it in your book there. A2U is alpha plus 2 beta. I got that from the reading somewhere. E1G is alpha plus beta. E2U, its energy is alpha minus beta. And that was in the reading somewhere. I'm not sure where I found that. Okay. So, does that make sense? So once you identify what the energy is of each orbital, each molecular orbital, multiply that energy times the number of electrons that are in that orbital. Page 416. You guys are too lazy to get up and walk around. Look at this. All right, this is where this is coming from. Right? This guy, he's Garada. He's not changing sign. Okay? Ungarada. Right? Garada. Okay. And then they found their pi energy for this thing, benzene. And it's just pi, so that's why they have only 6 electrons, because there's 3 double bonds. Okay. And each double bond is 2 electrons. So they have 6, 2, 4, 6. And there's 2 orbitals here for E1G, so he's not full until you put in 4. Yeah, he's full when you put in 2 because there's only 1, right? And in the reading, his energy is alpha plus 2 beta, his is alpha plus beta, his is alpha minus beta. So how do you get the energy, the pi energy, just for benzene, with 6 electrons, 2 times this guy's energy, 4 times this guy's energy. And then they did their math. Benzene anion, you can have one more up here. So you're going to have all this plus alpha 1 times alpha minus beta. And the cation, you have to take 1 away from here. So it's going to be this, but that's just going to be a 3 instead.
Oh, okay.
Okay? See, if we skipped the review and had the exam on Friday, we might be able to have some days at the end of the semester to watch our movies.
Oh, excited.
What? I'll even bring popcorn.
Bring popcorn to the test. When are we doing the instrumental final?
That's what we have to, on Friday, that's why I want to meet Friday. And I want to go, you guys bring all your old quizzes. We determine when you're going to take the final, give you all your labs back. You can even go look on the computer and see what all your grades are, right? Okay. No, I'm just giving you the grade sheets back. And you can look at the labs. I have them all organized over there. You can look at them. We'll find out. Because there's some zeros. There's some zeros. So, I mean, I don't know. I just know there's some zeros.
I know the Inversion. I'm going to give it tonight.
Okay. So we're good.